You think you know the most dangerous thing in space, right? If you've watched any sci-fi movie, the answer is always the same: a black hole. We are trained to picture them as cosmic vacuum cleaners, sucking up everything in their path: planets, stars, and maybe even us. But that image, while dramatic, is mostly wrong. Black holes are actually rare threats, especially here in our own galaxy, the Milky Way. Think about the massive black hole at the center of our galaxy, Sagittarius A. It weighs over 4 million times the mass of our Sun, compressed into a tiny region. Yet for us, 26,000 light-years away in the quiet suburbs of the galaxy, it is mostly a gentle giant. It is not gobbling things up in a frenzy. Most of the time, it is quiet. It only flares up occasionally when a random micrometeorite or a small gas cloud wanders too close and gets shredded, causing a temporary flash of X-rays. If the Sun suddenly collapsed into a black hole, don't worry, it won't. We wouldn't be sucked in. We would keep orbiting exactly as we do now, only it would get very dark. Its gravitational pull outside of the immediate vicinity would remain unchanged. We don't feel its gravity pulling on us at all. This changes everything we thought we knew. The most destructive things in space are not necessarily the biggest or the most massive. They are the things that produce huge amounts of focused energy, or the things that are simply too close for comfort. This brings us to a fundamental concept. In space, distance matters much more than size. Our protection is the vast emptiness between cosmic objects. Something the size of an apple on the moon needs a planet-sized telescope to resolve. That enormous gulf is our shield. So if black holes are out, what is the real monster we should be concerned about? Ask an astronomer what keeps them up at night, and they won't mutter about quiet, distant black holes. They worry about events that fire off blinding amounts of radiation at nearly the speed of light. A burst of pure, unadulterated energy that can wipe out life hundreds or thousands of light years away. If you look at the life cycle of a star, stars live their lives and then they die. Our Sun, which is average, will simply swell up and become a giant before leaving behind a cooling white dwarf. But truly massive stars, those that weigh 8 or more times the mass of the Sun, end their lives in absolute spectacle. These giants go out with a bang, triggering a catastrophe known as a supernova explosion. A supernova eruption outshines an entire galaxy of stars for a short time. For example, the supernova we saw in 1994, called 1994D, was almost as bright as the core of its host galaxy, which is made up of tens of billions of stars. The death process is messy and fast. The core of the star collapses and then rebounds, kicking out a shockwave that rips through the star's outer layers. This event creates nuclear fusion explosively in the core, making huge amounts of heavy radioactive elements, like nickel and cobalt, before blowing the material out into the cosmos. The material ejected from this explosion is accelerated to tremendous speeds, up to 3% of the speed of light. This explosion itself is a massive source of energy, called supernova shockwaves and radiation. This shockwave, traveling millions of miles an hour, slams into the surrounding gas in space, heating it up until it glows brightly in X-rays for thousands of years. But the remnants left behind are equally frightening. If the core collapse leaves behind a dense stellar corpse, usually a neutron star or a black hole, this corpse is incredibly compact. A neutron star is only about 20 kilometers wide, or roughly the size of a large city. However, it packs more mass than our entire Sun. Some of these remnants go on to become magnetars. Ask yourself this: what happens if a tiny, spinning, city-sized object is packed with a magnetic field 1,000 trillion times stronger than Earth's? That's a magnetar. These objects produce extreme magnetic fields, so strong they are thought to be formed during the violent supernova collapse. While they are not directly going to hurt us unless they are very close, they are a terrifying testament to the extreme physics of star death. It is this profound energy and chaos born from star death that sets the stage for the true cosmic threats, especially when that energy is focused and aimed. We now know how a collapsing star creates a violent, energetic mess known as a supernova, ejecting material at tremendous speeds and leaving behind objects like magnetars. But the physics of this explosion gets even weirder inside the core. When the iron core collapses, it happens in less than a second. the core shrinks rapidly from roughly the size of Earth to only 50 kilometers in size. The density in that core becomes astronomical, higher than the density of an atomic nucleus. This insane density causes a bounce, sending a shockwave ripping out. Neutrinos, tiny particles that normally pass right through matter without interacting, become trapped in the incredibly dense core. These trapped neutrinos heat the material around them, causing it to bubble up in a violent, chaotic convection. This neutrino-driven heating is what re-energizes the stalled shockwave and ultimately pushes the rest of the star apart. It is one of the most complex physics problems we know. This explosive force carries away almost all the energy of the event, most of it in the form of neutrinos. The total energy released by the supernova 1987A in the form of neutrinos was over 99% of the total energy output. That one event released an amount of neutrino energy equivalent to 10 to the 58th neutrinos hitting Earth. If we had neutrino-detecting eyes, we would be blinded by the sheer energy released by that supernova. The result of the explosion is a neutron star, an object so dense that a sugar cube of its matter would weigh hundreds of thousands of tons. Now, some of these neutron stars formed in the chaos of the supernova spin quickly and possess magnetic fields 1,000 times stronger than Earth's. These are magnetars, the strongest magnets in the universe. They radiate their power across all forms of light. The formation of this field is part of the ongoing physics problem of understanding supernovae. If a magnetar were to form too close to us, its sudden colossal magnetic field could disrupt electronics and strip atoms. But the real immediate danger comes when a collapsing star fails to explode cleanly and focuses its remaining power. Think about this. What if instead of a spherically shaped explosion, that chaotic core collapse produces a narrow, tightly focused beam of energy shooting out from the poles of the star? This leads us to the terrifying reality of gamma-ray bursts. Gamma-ray bursts, GRBs, are the brief, most powerful confirmed events in the entire universe. They are ultra-relativistic jets, meaning they are tightly collimated streams of matter and energy moving near the speed of light. They are so energetic that they can be spotted by amateur telescopes, even though they are billions of light years away. A GRB occurs when a massive star collapses and forms a black hole or a rapidly spinning neutron star, and the enormous energy released is channeled into two opposing jets. When the jet punches out through the star's outer layers, and if that beam happens to point directly towards us, it's a very bad day. We are protected from most GRBs by two things: distance and focus. First, distance. When we look at a quasar, an accreting black hole, we see light that has traveled for billions of years to reach us. We are effectively looking into the past. GRBs are so bright that we see them from the early universe, but this is where the inverse square law and distance saves us. Second, focus. Unlike a supernova that explodes in all directions, a GRB is highly collimated like a laser. The beam is only a few degrees wide. The chance of one happening and being pointed directly at Earth is extremely low. The power released in a GRB is mind-boggling. They release more energy in mere seconds than our Sun will emit over its entire 10 billion-year lifespan. If a GRB were to occur within a few thousand light-years of Earth, the burst of X-rays and gamma rays would strip the ozone layer from our atmosphere in seconds. The resulting ultraviolet radiation shower would sterilize the surface of the planet, wiping out life. While GRBs are tiny in terms of size, the jet launching region is compact. Their ability to focus energy makes them far more dangerous than any distant, quiet black hole. The quiet black hole is just a dent in space that you have to fall into. The GRB is a shot of pure radiation designed to fry things across intergalactic distances. This idea that distance is our only true shield brings us to another set of dangers. Cosmic objects that are not immensely powerful but are simply too close. We now know that powerful focused events like GRBs pose an existential threat if they happen close by. But how close is too close? For a GRB, even a distance of many thousands of light years might be too close. Luckily, GRBs are exceedingly rare in our modern corner of the galaxy. Astronomers have measured the rate of supernovae in the galaxy to be about 1.63 per century. While that sounds frequent, we haven't seen a naked-eye supernova in our galaxy since 1604, meaning that our view of the galaxy is somewhat obstructed, or the event happened far away. Supernova 1987A, the closest seen recently, was 160,000 light-years away. Distance saves us. But what if the danger isn't enormous energy, but rather something dull and massive just wandering too near? This brings us to rogue stars and cosmic encounters. Our Sun and solar system are not stationary. We are hurtling through the Milky Way at a tremendous speed, orbiting the galactic center once every 250 million years. As we move, we constantly approach and recede from other stars. Most are far away, but some pass close enough to pose a problem. These close passages are not science fiction. They are a predictable result of motion in the galaxy. For example, Gliese 710 is an orange star located in the constellation Serpens. It is currently approaching us at nearly 32,000 miles per hour. In about 1.29 million years, it will pass within 10,500 astronomical units of our Sun. An astronomical unit, AU, is the distance between Earth and the Sun. While that sounds like a huge distance, it is only about 100 times the distance to Pluto. Gliese 710 is not expected to disrupt Earth's orbit directly. The real danger is its effect on the Oort cloud. The Oort cloud is a massive, distant reservoir of icy debris surrounding our solar system. The passage of Gliese 710 has the potential to disrupt the Oort cloud, sending a massive shower of comets plunging inward toward the inner solar system, where we live. This could lead to a comet shower that lasts for millions of years, posing a real persistent impact risk to Earth. The rogue star encounter is a mundane event in cosmic history, yet it represents a higher probability of catastrophe than a GRB. This constant stellar motion is how rogue objects end up in our system too. We have observed strange interstellar visitors like Oumuamua and 3I/ATLAS. Oumuamua was the first interstellar object detected, speeding through our system on a path too fast to be captured by the Sun's gravity. Its movement defied explanation by simple physics, suggesting some other force or mechanism was acting on it. 3I/ATLAS, a more recent visitor, is an interstellar comet that is particularly interesting because it originated from the ancient, distant regions of the galaxy. It is incredibly large, 10 times the size of Oumuamua. These objects remind us that our solar system is open to unexpected cosmic encounters, where high speed and unexpected trajectories, rather than extreme energy, define the danger. So how likely are these dangers, really? For a localized cosmic encounter like Gliese 710 causing a comet shower, it is certain to happen. We just have to wait a million years. For extinction-level events like a nearby GRB, the chance is incredibly small, but the result is total. The immense scale of time and space makes most catastrophic events low probability, though they are certainly real. But there is one final threat, a truly abstract danger that makes even the violent death of a star seem small. The possibility that the foundations of reality itself are unstable. We have covered threats ranging from the highly energetic, gamma-ray bursts, to the imminent rogue stars. But the most profound danger comes from theoretical physics, involving a phenomenon known as vacuum decay. This concept proposes that the universe we experience might exist in a false vacuum, a temporary, unstable energy state. If this state were to collapse into a true, lower energy state, it would trigger a reality-altering bubble that would expand at the speed of light. This bubble of true vacuum would fundamentally change the laws of physics inside it. As this bubble expands, anything it touches, stars, galaxies, and even us, would be instantly destroyed or transformed into a new state of matter governed by different unknowable laws. This is theoretical, serious physics, but unlike GRBS or rogue stars, vacuum decay would offer no warning and no defense. It is the ultimate end of reality scenario. While the mathematics of vacuum decay is far removed from star counts and orbit prediction, the underlying quest for understanding fundamental stability is what drives many major physics projects, like the search for gravitational waves from the Big Bang. Now let's circle back to what astronomers actually worry about on a practical, day-to-day level. They are often focused on the subtle signals from distant, violent events. 1. Tracking gravitational waves. Astronomers are mapping the universe by listening for gravitational waves, ripples in space-time created by massive objects merging, like two black holes crashing together. The LIGO experiment was created to detect these waves. The massive collision of two black holes converted 3 solar masses of energy into gravitational waves in a fraction of a second. These events are detected billions of light-years away. Future projects aim to map the gravitational wave background from the birth of the universe and phase transitions, pushing the boundaries of what we can observe. 2. Observing high-energy objects. Astronomers closely monitor high-energy sources like quasars, which are powered by accreting supermassive black holes. They look for the light emitted from the accretion disk just before the matter falls past the event horizon. They worry about understanding how these objects form powerful jets, highly focused beams of plasma and energy that extend far beyond the galaxy. These relativistic jets are incredibly powerful, and understanding their production mechanism is a central problem in astrophysics. 3. Predicting cosmic collisions. As discussed, astronomers constantly monitor the positions and speeds of stars and objects like Gliese 710 to forecast future near misses and potential impacts. We are constantly surveying the sky for objects that could become problems. The most concerning thing about all these massive, destructive events is that their probability is entirely determined by their proximity. An event that happens 1 million light-years away is just data. An event that happens 1,000 light-years away is an extinction-level event. Let's summarize the true cosmic hierarchy of danger. Black holes are scary only in movies. They are only dangerous if you fall past their event horizon, which, given their tiny sizes relative to the distances in space, is highly unlikely for our planet. The real dangers are either explosively powerful and highly focused, or slow-moving and locally disruptive. 1. Directed cosmic artillery, gamma-ray bursts. The most devastating known astrophysical events are GRBs. They are beams of pure energy that, if aimed at Earth from relatively nearby, within a few thousand light-years, would sterilize the planet by stripping away our ozone layer. The physics of GRBs is serious, resulting from the catastrophic collapse of a massive star, channeling its death throes into a focused stream. 2. Galactic traffic accidents, rogue stars. While less dramatic, the passage of a rogue star like Gliese 710 is a certainty on a cosmic timescale. The resulting shower of comets and space rocks would present a persistent, long-term threat of impact to our planetary home. 3. The end of reality, vacuum decay. The ultimate unavoidable theoretical risk is the decay of the universe's energy state, changing the laws of physics instantly. Luckily, we have no reason to suspect this bubble is coming, but its possibility stems from serious questions about the nature of reality. How likely are these dangers, really? Extremely unlikely to cause immediate catastrophe. Our solar system sits in a rather calm, resource-rich region, safely between the violent spiral arms of the Milky Way, shielded from the worst galactic activity. We are protected by the immense distance between stellar objects. The likelihood of a high-energy beam from a GRB happening in our local stellar neighborhood and being perfectly aimed at our world remains astronomically small. However, astronomers continue to monitor these threats because they represent real, observable physics. They track the afterglow of supernovae, the incredible energy output of magnetars, and the predictable orbits of nearby stars that will one day disrupt our far-off cosmic cloud. If you want to understand space like a NASA-level analyst, quick without studying for years or paying thousands for a university degree, we have a community that will help you. Link is below. So the next time you look up, remember that the most terrifying things are often those you can't even see the focused beam of a star's death, or the slow, silent approach of a rogue sun. These cosmic events prove that physics is far more complex and far more dangerous than the simple image of a passive black hole. If you are curious about the origins of these massive stars that die in such spectacular fashion, you need to understand where they first appeared in the cosmos. Click here to learn about the first stars in the universe.